It's now time for our next equilibrium constant. So we've learned Kc when using concentrations. We've learned Kp when using pressures. Now it's time for Ksp. Now Ksp actually does still use concentration. So this is sort of you could call it a subset of Kc, but it's specifically having to do with saturated solutions, and more specifically, I guess a better way would be to describe it as a way to tell how much solute can dissolve in a solvent. We know that even table salt, if you take an entire container of salt and pour it in a small cup of water, it won't all dissolve. So this is an indication of how soluble a salt is. Now, back when we did solubility rules, we didn't have to learn all the exceptions to solubility rules, but we're going to be dealing with a lot of things that are considered to be insoluble, meaning they don't dissolve. However, even things that are considered insoluble still might dissolve a little bit, just a tiny bit, and KSP can show us that. And the ideas of the big and small values will all still be the same. It's just that we're applying it to a solid dissolving. Now you have some pictures on your paper there, but I've got an animation that I'm going to use to give you a better idea of the dynamic equilibrium that is achieved in KSP specifically. So if you take a look at this little animation that we have here, you've got water, the shaker has some sort of salt, and we're using a salt, you can see it by the label, that is slightly soluble. So one that will dissolve a little bit, but not a lot. So what happens, you see when I shake the shaker, some of the salt comes out. As soon as it goes into the water, it all dissolves. Okay, you see it's all broken up from itself, it's moving around, randomly. I let another one go, and we still get dissolving. Okay, it looks like all of it is dissolving. Actually, we've had a little bit trying to adhere down to the floor, but not that much. Now, if I let this one go, we'll probably start to get some insoluble. So you see some of it break off, but you see the large majority of that chunk hit the bottom. Now, that big chunk that's down at the bottom, let me see if I can write on this. You see where I put my arrow right here? This big chunk right here is the solid, and all the stuff that's moving around is the dissolved part. Now keep an eye on the chunk for a second, and what you're going to see is you'll see some particles all of a sudden become a part of the chunk, but then at the same time other particles are going to break off. So you see that interchange that's happening. That's the dynamic equilibrium. If you measure the concentration of this solution right now, concentration being how much of these are dissolved, right? How much solute you have dissolved in your solvent, it would be saying the same. Yet look at what's happening. You can see that interchange back and forth. So KSP is measured once we've reached dynamic equilibrium. And this thing right now is at dynamic equilibrium because it's exchanging back and forth at equal rate. Okay, and again, I can put more salt for those of you that just like watching it fall in there. Look, very little of it dissolves, sinks down to the bottom. Now we're going to get more of that exchanging back and forth. So the idea of dynamic equilibrium is not that it just stays constant, which it does, the concentration says constant, but there is still an exchange of particles going on. The particles aren't going to stop moving. Okay, so you've got your example here of what it looks like. Now, the beauty of KSP is that it's still going to be like K, we're still going to do products over reactants, but if you take a look at an equation that we'll be doing for KSP, they look like this. So you've got your solid, so let's say that solid we were dropping in there was BaSO4. So you've got your solid, you're putting it in water, so the equation is simply a dissociation equation. This isn't an actual reaction, this is just dissociation. So you're showing it break up into its ions, okay? So BaSO4 breaks up into Ba plus 2 and SO4 minus 2. So this is all about ionization, okay? So remember, we've got it right here, you're taking a solid and you're turning it into ions. So they're not going to give you the equations. They're just going to tell you you put solid BaSO4 in water, and you're going to have to know that you need to write that equation. Now, writing the KSP equation, watch how easy this is. So we know that all Ks are products over reactants. So we're going to do the concentration of Ba plus 2. That's our first product here. It's at an exponent of a 1, so I'll leave it as a 1. And then SO4 minus 2 also has an exponent of a 1. Now that's the products, they go on top, and reactants go on bottom, but what have we got here? Oh, disappeared. What have we got here? A solid, Do we put solids in equilibrium law? The answer, of course, is no. So this is your KSP. There is no bottom, or you could think of the bottom, I guess, as just being 1, because the only reactant we have is a solid. And if you look at that, most of the time, equations like that make the math a little easier. Not always, we might still need to use quadratic, but it's still the exact same idea. So again, you're not going to be given the equations on KSP. You're going to have to write them for yourselves, but really all they are dissociations. So just dissociate your solid. And then when you write your KSP, products on top, which will be your ions, and reactants on bottom, but there's no reactants to put in. Remember, the other reactant in this problem really is water. We don't really show it in the equation because it would end up canceling out on both sides because it's sort of the constant in here. And so again, that's where it went. But the fact that it forms aqueous, you know that water was present. So that's the underlying idea. Now there's a couple other things we need to know and understand. First of all, looking at a KSP value tells you a lot, and it's very similar to what we learned before. If you remember when we talked before, we said that large K values meant lots of product. Okay, large K values mean lots of product. So in this case, the product is the ions. So if you have a large K value, a large KSP value, then that means the solid is really soluble, because lots of product means lots of ions. Lots of ions means really soluble. If it's a small K value, then that means that it's not very soluble. And again, some things, even if they have a K value, are still considered to be insoluble because so little of them actually dissolve. Maybe you put 1 billion molecules in water and 4 of them dissolve. That's not enough for them to deem that thing as soluble, but technically if we calculate the K value, we would see that some actually did. So that BaSO4 problem that we just did, if you look right here, the BaSO4's KSP was 1.1 times 10 to the negative 10, and that's telling you that very little BaSO4 will actually dissolve. Okay? And again, that can be really useful for us because although only a little dissolves, we still sometimes need to know how much actually did. So you definitely want to learn this, but you probably already know it. As long as you understand what these new equations are saying, the dissociation of the ions, so you already know what big and small K values mean. Okay, a couple of definitions, and